Okay. All right. So, okay, this is next time. This is the next lecture in the sequence. Let's talk about, let's talk about what we've talked about, and then we'll talk about other things. So, I think the way that I'm going to work it today is we'll implement insertion sort, which is what I promised last time. We'll do a little bit of merge sort, which is, I think, my favorite. We'll do quick sort, which is pretty quick. And I think we'll leave off heap sort until we talk about heaps. And the reason for that is because heap sort and heaps are basically the same thing. Apparently, in the history of heap sorting, they were developed at the same time. They basically use the exact same structure. And I was thinking of doing this as like an introduction to it, but then I realized that if I do this, then I'm basically going to be covering the entire topic. And Project 1 was released. Will we discuss that? I might not discuss that right now. I might discuss that maybe next Tuesday. I think the Project 1, right, is going to be due. Let me find it. In my. Let's hope that I can find it easily. So Project 1 is out. Basically, you're going to have to implement a linked list data structure, and you're going to have to implement a function that basically compresses sparse matrices. I think I might wait until next Tuesday to discuss it. The due date for this project is all the way out at September 29th. So I think what I'm going to do instead is just wait a little bit on this, probably. The reason why I might do that is that I'm probably going to try to implement the thing over the weekend, and then I will have a better idea of all the details. I think, yeah, so I'm going to look more carefully at all the details and get it implemented, and then I'll tell you about what I think. All right. So, I promise you there's plenty of time, right? September 29th is pretty far away, so I think that we can skip it for a day, or until Tuesday, and it'll be okay. When is next Tuesday? It'll be the 15th. That'll be the due date of your... are you able to submit Project 0 now? I haven't received anything from Cash. I think he's going to probably open the submit directories today. I'll probably be around for a bit of tech support on that, unfortunately, but I will try to figure out if Project 0, I'm sure at some point today, the submit directory will open up for it. So I might be sent an email. If I'm sent an email about it, I will send you an announcement that says it's open now, and then you can copy your file into your directory. So I think that's probably how it should work. Until I receive anything, just assume that he probably hasn't set it up yet. So, yeah. He's probably just working on it. So this is what we're going to do today. We're probably going to do insertion sort, merge sort, quick sort. I think I'm going to show you just an example of an algorithm that runs an O of 2 to the n. Maybe basically an example of something that's similar to that. And maybe we'll do some binary searching. Okay. All right, so let's get about it. So the first thing I should do is I defined big O last time, but I want to define big omega and big theta this time. And the reason why I want to do that, and I think it's good that I didn't define them together. So recall that F is big O of G when eventually G is bigger than or equal to F, and well, really, I guess a constant times for a constant we invent. So the mathematical way to say this is that F is big O of G of N, and I guess I'd put an F of N then. F of N is big O of G of N when there exists a constant C, probably bigger than 0. There exists a constant N0, so that for all, which you can say for all N bigger than or equal to N0, then F of N is less than or equal to C times G of N. So what this generally means, this part here, right, is the eventually part. And this part is just saying that F is bounded above by some constant times G. So okay, cool. So what is big omega? Well, big omega is the opposite. It's a little dangerous to say the opposite, but it's basically the opposite. It's the opposite of big O. And so I don't know. I don't know where that's from. I'm missing a reference. So the definition is almost exactly the same. Basically, the definition is eventually I should say F of N is omega of G of N when eventually F of N is bigger than or equal to a constant times G of N for a, okay, constant we invent. So basically the way to think about it is that O stands for like overshoot. And you see how there's these little feet on omega, that means it's the lower bound. And so basically the way to think about it in terms of time complexity, so this is what it does in terms of functions. So if a function overshoots, so if our algorithm takes f of n time, then an overshoot of that function would be like the worst case. Or even worse than the worst case, right? Because it could be a higher order function. So we could always say that n squared is big O of n to the fifth, like this, because n to the fifth is always, well, not always, a constant times n to the fifth is eventually bigger than n squared, so this is true. Or it can be worse than the worst case. Basically, this is like at least the worst case, right? And the lower bound is kind of a similar thing. It's either the best case or better than the best case. And so generally, when you write that an algorithm is big O of something or big omega of something, you're trying to tell somebody that it is pretty tightly bounded by those things, because obviously, well, it's not obvious, but let me show you an example. So basically everything except 0, I guess, is basically big omega of 1, right? And by everything, I mean all the functions that we really use in computer science, right? LG, which remember, so, well, don't remember anything yet. When you write LG, it is equal to the log base 2, right? The natural log is equal to the log base E, right? Where E is equal to 2.718 ... right? It's an irrational number, but it's approximately equal to this. And when you write LOG, there's a little bit of ambiguity, but generally you mean the log base 10. A big O of existence. I like that. That's pretty creative. But anyway, so basically everything is omega of 1, and let me just tell you the kinds of things that are omega of 1. Constants, right? Because any constant, say A, and remember that big omega is the opposite. So if we say that this is omega of 1, what we're actually saying is that A is bigger than or equal to, not less than or equal to anymore, right? It's the opposite direction of the inequality, is bigger than or equal to some constant times 1. Well, basically what we can do is just make, C is equal to, I guess, A minus 1 most of the time, right? Unless A is equal to 1, then you just make it like 0.5 or something, whatever. Or like C is equal to A divided by 2 or something. Whatever you do here, this should be okay. As long as A is bigger than 0. Assume that A is bigger than or equal to 0 at least. And so, because, I mean, to say that you're going to take negative time, like, there's certain functions that we don't really talk about in computer science. For instance, like, minus n squared is usually not the running time of any algorithm. And the reason for that is because that would require you to take negative time, right, to run. So that's like, if you run this algorithm, 2 days are rewarded back to the computer that you can then use for other algorithms. That would be a breakthrough in physics, and I would want to know what you were doing. So basically, we generally don't use like negative algorithms. A lot of algorithms, or a lot of functions like 1 over n kind of things, you don't see a lot of this type of behavior, because that would require that as n goes to infinity, the amount of time that the algorithm takes goes to 0. Generally, that's also not something... I guess if I mean like A in the class, sure. If that's a joke, yeah, sure, A is the best case. Well, so basically... no, I'm not going to move the camera screen. Instead, what I'm going to do is I'll just write log base 10 here, and then I just won't use this space here. I'll just try to remind myself not to use anything in there. So basically, polynomials are always bigger than or equal to some constant c eventually. Again, that's requiring that they have a leading coefficient that's positive eventually. Exponents or exponential functions are always bigger than some constant c. So basically everything is big omega of 1. And I technically have to use scare quotes. If you're some mathematician, you're going to say, well, I could come up with an infinite collection of functions that is not big omega of 1. Okay, you win. But what I'm saying is, like, all the functions that we talk about in computer science are basically big omega of 1. And so it basically goes the opposite way. Remember how I was talking about the families of functions before? How I was saying that you basically have constants, and then you have, like, logs, and then you have roots, and then you have, well, let me just be very careful here, and then you basically have n, right? And n is kind of dividing point, and then you'll have, like, n log n, which I know you're like, well, why are you specifically calling out n log n? And there's a reason for that. And then basically you have higher polynomials, like n squared, even n to the 1.5. So there's a fact, I think I said this fact last time, but there's a more general fact. There's a more general fact that says that, like, the limit of the log of n over n to the epsilon is equal to 0, where epsilon merely has to be some power bigger than 0. So epsilon could be, for instance, 0.0001, and eventually n to the 0.0001 power is going to beat log. And so in computer science, there's also some really good news. You can be a little bit uncareful about the base of your logarithm, and the reason is, and let me just finish this before I say this. So higher powers like n squared, n cubed, and then you have, like, exponentials, and then you have, like, super exponentials, right? And super exponentials are things like n factorial and 2 to the n. So we can come up with an algorithm that runs in n factorial time. In fact, that algorithm is the recursive calculation of factorial. And then there's a 2 to the n algorithm that I have in mind, which is the recursive Fibonacci numbers. It's not exactly 2 to the n. Technically, it's like phi to the n, where phi is equal to 1 plus the square root of 5 over 2. But it'll serve our purpose because, it's close enough. So anyway, the point is that you see all these bigger than signs, right? Constants are going to be less than logs, are going to be less than roots. So basically anything that's in the set of constants is going to be big O of something that's, or I should say, anything that's a log is big O of a constant, anything that's roots is big O of logs, anything that's n is big O of all these things. So big O basically says that if I'm bigger than you, then I am big O of all the things on this side. So big omega works the exact opposite way. So basically, constants are big omega of everything. Logs are big omega of all the stuff that comes after it. Roots are big omega of all the stuff that's bigger than it. N is big omega of all the stuff that comes after it. So basically, you could say something like n is big omega of n log n. And that's true. Okay. So, and then let me quickly define theta. So let me define big theta for you. The good news is big theta's definition is pretty simple. Big theta is just big omega and big O. So what it means is that instead of having one constant, there's actually two constants. There's a C1 g of n is less than or equal to your function, f of n. Whoops. And let me just draw in my little box here. No, do not draw there. So okay, so basically, what being big O and big omega is that you're both a lower bound and an upper bound if you use two different constants. And so the way to talk about this, normally mathematicians will say that this thing is tight bound, or tightly bound, or something. They might use the adverbial form, they might not. It's a tightly bound relation between two different functions, right? So you might say that f is theta of g when it's tightly bound like this, when basically there's some n0 such that when n is bigger than n0, the function f sits between them. So the way to think about it is that a tightly bound function is going to look something like this. So this will be c2 times g, this will be c1 times g, and this will be the function f. And so f could be some function that we don't particularly have a great algebraic understanding of. F could be some function that wiggles around quite a bit. As long as it eventually sticks, as long as this is like n0, as long as after n0 it just sticks between c1 of g and c2 of g, then we're safe. That's all that's required. So, yep. All right. So we'll do more examples of big O, big omega, and big theta. I think what I'm going to do on the homework that I have not written yet, but when I write the homework, I'll probably release it maybe this Friday or sometime. So like homework 1 is probably going to be released this Friday. It's going to be basically like linked lists and big O. And by big O, I mean omega and theta. And so it's going to be like a bit of math. So this will be the math part, and this will be the coding and problem solving part. And so basically I want it to be about 50-50 of each, so that you have like a good understanding of, and I probably will also use some code for the big O part to be like, what is the algorithmic complexity of this thing? But it's going to be simple. It won't be something that's really complex. It'll be something similar to what we've done in class. Okay, so now that I've talked about big omega and big theta, we should talk about insertion sort, right? So let's go and talk about insertion sort. So here's something that we insertion sorted last time, so who cares about that? Let's insertion sort this a new list again. So create maybe a random list. Random. There we go. And now let's sort it. To remember just what insertion sort does, and then we'll implement insertion sort. And then we'll move on to some of the others, the two last sorts. We'll do merge sort and quick sort. But for now, let's just do insertion sort. So what does insertion sort do? It picks an element, and it shifts it back as far as it needs to go. So where's my mouse? So you see here, it's going to shift 21 back 2 places, and then insert it here. And see, it knows that this list, let me just stop it right here. It knows that this beginning part of the list is already partially sorted. That's the assumption that we make as we go through. So as it's going to shift something back, it knows that as long as the elements are bigger than it, it can shift it back. And as soon as the element becomes smaller than it, it knows it doesn't have to search anymore. Because once it finds 22 here, it's going to say to itself, well, I'm good because I know that this list is partially sorted, so this part here is going to be, I don't care if it's 21, I don't care if it's 17, we don't care what it is, we know it's less than 22. So I know my place is now here. So basically it's going to shift 39 up, and then it's going to insert itself. See, it sees 22, and it's like, okay, I'm done. Here it'll see the 39, and it's done. Right, and here it sees 39 and it says, I don't need to shift. And then this will say, I don't need to shift. And then this will say, I need to shift quite a ways. It'll be like, okay, let's go. Let's turn up the speed a little bit so we can get to the implementation. And in, right? There we go, 28. It shift. Let's turn up the speed a little more, right? It just shifts itself back until it is in the right place. This one doesn't have to go very far. Thankfully, the 40s don't have to go very far. But unfortunately, we're going to have to do a lot of shifting when we find this 8, right? Because this is the one danger of insertion sort. So the one danger, well, I shouldn't say danger. This is like towards the worst case of insertion sort is when basically the list is like reverse sorted. Because in that case, it's going to have to shift every element as far as possible in order to get to the correct position. So here it has to shift this all the way back to the other 27. I think it probably sees it and doesn't shift because that's one less step it can do. Yep, so basically here it knows it has to go basically all the way back to the beginning, which, you know, is unfortunate for the poor thing. This is if this happens all the time, then we get towards the worst case of insertion sort. But insertion sort does perform better in cases where the lists are at least partially sorted towards actually like very sorted. So its best case is actually on a sorted list, which is a good thing. So experimentally, I think I read this in either a paper or Wikipedia or some combination of that basically what ended up happening, the reason why insertion sort became so popular was that they did a study on the actual lists that were being sorted by algorithms. And as it turns out, most of the time, the lists that are being sorted are at least partially sorted already. And that's why insertion sort does better than its worst case in the case of a lot of sorting algorithms. So, or in the case of a lot of lists. So let's implement it. So let me put a bunch of space in here so you can't see merge sort yet. Or even better, why don't we just move insertion sort below merge sort to the bottom? I was thinking maybe we'd talk about bucket sort. Bucket sort is kind of a cute little sort that sometimes people say it runs in O of n time, which is kind of true. Yes, it's it's a little bit more complicated than that. It actually runs in like O of n plus n squared over k plus k time, where k is the number of buckets. And I can talk to you about that when we get to it. But anyway, let's write insertion sort. So So remember that insertion sort is the, like, you pick an element and you move it back as far as it needs to go. So the outer loop needs to be for, well, I guess we can, so I'll tell you that in just a second. So I is going to be the element we pull back as far as we need to. So I'm going to do something that might seem a little dangerous, but I think it's okay, as long as I can start it at I is equal to 1 instead of starting at I equals 0. And the reason why is because if I just look at a single element in a list, we can't pull it back, right? So it's in the right position. So the first element is always in the right position because it's the smallest element in the list of size 1. Okay. On the other hand, what we need to do inside of here is usually people write this as a while loop. So I'm going to write this as a while loop. So what do we do while? So basically we have to go while we need to pull the element back a position. So how do we know if we need to pull the element back a position? So first I'm going to set j is equal to I, and you're going to be like, what's j? There. J is an integer. So while the list sort at j is bigger than, is less than the list sort at j minus 1. And you'll see why I'm doing j minus 1. And so the other thing we need to do is ensure, before we do this, remember that when we get to the end of the list, j could equal 0, because what we're going to do is we're going to do a j minus minus in here. Here we're going to do the swap elements forward business, and then we have to go back an element. And that's how we do it. We go j minus minus. So the real question here is, how do we ensure that this is safe to do, right? Because if you plug in 0 here, this will be okay. But this is not going to be okay, right? This is going to die. So what you need to do is you need to say, while j is bigger than 0, and, right? And this just makes sure that you're only ever getting to the element where it's possible to shift backwards, right? So, okay. Let's make an int element, and so we can say element is equal to list to sort at I. And then what we get to do here is when we swap elements forward, we don't actually need to stick the element into the position at every time. We only stick it in at the very end when we've finished swapping back. So let me show you what I mean by that. Because remember, if you look at the way that the algorithm was working, it was basically only shifting things back, and then it would insert the element into the correct position. So it would only insert the element once. So basically what we get to do is we get to say, if the list to sort is this way, then we get to say the list to sort at j is equal to the list to sort at j minus 1. And so what we're doing is we're actually overwriting the element at j, and now it's identical to the previous element at j minus 1. And so then when we go back, we'll make the element j minus 2, we'll push that into the element j minus 1, we'll push the element j minus 3 into j minus 2, until we don't need to do it anymore, right? This is saying, as soon as, while the list to sort at j is less than, right? And remember that if the list is sorted, then it should be bigger than or equal to. So this is the bad condition, right? Okay, so cool. And then at the very end, we get to say that list to sort at j, wherever j ends up, right? It could be 0, or it could be anything between 0 and I, right? So it actually could just be I. Technically, you might even want to do a safety check, but I'm not even going to do that. I'm just going to say list to sort. No, I'm sorry, not list to sort, element, right? Because at this point, element has been overwritten, right? Because we pushed the elements from the list up by 1 in their position. And so element is the only thing that's been erased. And so there we insert it, and at that point we're done, right? So that's insertion sort. Insertion sort basically takes an element and it shifts it back as far as it can go in the partially sorted list, and then it just assigns it to wherever that position is. Okay? And so that is insertion sort. Now, let's calculate, right? So that's the point of this class. So insertion sort itself is not the point of this class, right? The point of this class is to understand the complexity of insertion sort. And so how do we understand the complexity of insertion sort? Well, what we do here is we say, all right, this loop here is always going to run technically n minus 1 times, but you know that I can basically ignore those extra little constants. So this loop is always going to run basically, nope, this is not Python. Always going to run n minus 1 times. I'm just going to say n. Right, I'm overestimating a little bit. You might be like, yeah, it's technically a little inaccurate, but you know that big O is going to have a giant constant c in front of the function anyway, so it's going to ignore a lot of these like lower order details. Okay, and then how many times is this loop going to run? This loop is going to run, well, anywhere between 0 times, where it just runs the check, up to n times. Well, I mean, yeah. I guess actually up to I times, where I, right, goes from 1 to n. So let's calculate the worst case and the best case in both possibilities, right? So if you have, let's just think of what happens if you have a completely sorted list. If you have a completely sorted list and you throw it into insertion sort, what ends up happening is that this never is true, right? It's never true that the thing at further on in the list is less, right? It's always bigger than, because it's always sorted. So this while loop actually only ever checks basically this if statement here, right? And so it never actually executes. And so the good news is that if this never executes, it's just as the check, that's like an O of 1 operation. And how many times are we doing that O of 1 operation? We're doing it n minus 1 times. So basically the way to think about it is, so the insertion sort best case is basically a sorted list or close, right? It could be a partially unsorted list as long as it's pretty close. And so the way to think about it is that if n is large, if you only ever have to shift elements maybe k times, and then you say, well, the best case is, let's say we only have to shift elements k equals 1 time or 0 times, right? Basically, k equals 1 is just checking the loop condition, which does take time, right? You actually do have to check the loop condition once. And so even though it doesn't execute the extra code, let's just call that 1 rather than 0. Otherwise, this function is going to take no time, which is not correct. So basically, right, so you do k equals 1 checks. And so basically, if you have n minus 1 times k, which is equal to 1, then you basically just have n minus 1, which is O of n, right? And so in the best case, or I shouldn't say O of n, I should say, technically in this case it'll be omega of n because it's the best case. And so the reason why n minus 1 is omega of n is because you can adjust the constant c so that, for instance, n minus 1 will be bigger than or equal to, for instance, say 1/2 n, where now the constant c is 1/2, right? So it's possible to make that, as long as the constant c is bigger than 0, you're okay. So in this case, we just need to make the constant c 1/2 in order to make n less than n minus 1, right? Because otherwise, if you keep the constant c bigger than 1, then n minus 1 is always going to be bigger than n, and you're kind of running into a problem. So this is the best case. So the best case is actually really good for sorting algorithm, because if you think about it, a sorting algorithm definitely cannot be better than O of n, or omega of n. And the reason why it can't be better is because you at least have to visit every element once, right? So if you, even to determine, right, this is not even to sort a list, but even just to determine if a list is sorted, then well, I wouldn't say 1 minus n. You would say n minus 1, right? Because 1 minus n is probably going to be negative. Right? You have to restrict it to n minus 1. Well, you can still say n minus 1. It's true, you can say that, but I mean, the point is that in most computer science textbooks, you can say it's omega of n minus 1, and that's fine. But most computer scientists will drop this lower order term pretty quickly, because they'll just say, well, actually this algorithm probably takes something like 2n minus 3 or something like it. It's hard to say exactly, so you'll just say that this thing is equal to omega of n. So, okay. basically, what else do I want to say about this? Right, so this is the best case. So the best case is omega of n, and that's actually the best case for any sorting algorithm, as I said, because it's impossible to sort a list without at least visiting every element once. So, if you can come up with a way to prove that a list is sorted without visiting every element at least once, I'd like to hear about it, right? So that's the kind of idea here, is that this is kind of as good as it can get for a sorting algorithm. Now, what's the worst case, right? So the worst case involves the Gauss sum again, right? Because you know that what's happening is we're going from I is equal to 1 to n, and you know, for instance, here that we are taking I steps, right? The worst case is if this has to run as many times as it can, right? And so it's going to run up to I times. So I is dictated by this outer loop. The outer loop, so a for loop, when you translate a for loop, basically a for loop or a while loop usually translates into summations of the internal cases. So that's why I do this. Anyway, so basically this is this, right? Literally this. I mean, technically, you might say it's 3i because there are 1, 2, 3 statements here, and then there's this extra thing, but this is outside of the internal loop, so maybe this is, when you do this, it's 3 plus 3i, or something like that, and so this thing is equal to 3 plus 3 times the sum of I up to n, starting at I equals 1, and so this is the Gauss sum, which is equal to 3 plus 3 n plus 1 over 2. And the good news is that when you get done with all this mathematics, all of it just tells you that it's O of n squared, or really O of capital N squared, because that's the variable I've used. And so this is why we usually call insertion sort a quadratic sort, right? This makes it a quadratic sort. But, just because it's a quadratic sort doesn't mean it's always going to perform in its worst case. So the interesting fact about insertion sort is that on small lists, it actually does perform pretty well, usually. On lists of, I think it's like lists of size less than 50. Sometimes they don't use the n log n sorts, they'll use insertion sort. I think the reason why I say that is because Python, the dot sort method in Python is it's a merger between merge sort on big lists and insertion sort once the lists reach a certain size. So basically, merge sort will break up your lists into sublists, and I'll show you how that works in just a second. And then insertion sort actually takes over and sorts the small list. And I think they have some kind of cutoff. I know the cutoff is at least less than 50. It might be 50, but I forget the exact details. The point is that insertion sort can perform better on smaller lists. It usually performs better on lists that are already partially sorted. So if you have a completely randomized list, you're probably going to get towards the worst case quadratic performance. If you have a partially sorted list, then you will get towards the best case. And you could maybe do an average case, right, where the thing is partially sorted and maybe partially not sorted. So you might say, I'm going to average over all the possibilities. So maybe you're going to average over n times k, from k, when you add up k, meaning from 1 to n, and then you divide by the number of things, which is n, you're going to end up with n times n plus 1, or technically this, which is, when you cancel this out with this, you'll get n times n plus 1 over 2. This is a very rough average. The average case would be about quadratic. But if you assume that there's only k swaps, then the algorithm becomes O of n times k, which is slightly better than O of n squared, right? If k is like, 10, for example, and n is going off to infinity. If n is like 10 to the 6th, right? We're sorting in a list of 1,000,000 elements, but k is only 10, then actually this does perform better than quadratically. But you don't have to worry about this average case business. Well, maybe I'll make a problem about it or something, but this is just more amortization. But this is a very rough kind of estimate. All right, so let's talk about merge sort. So merge sort is, I think, of all the sorts, I think this merge sort is my favorite. I don't know why. I just like it because for me it's really simple to understand. And I don't know. I actually always had a problem with insertion sort. I would forget what insertion sort did. Back when I was an undergrad, I'd be like, what on earth does that do again? I remember selection sort because that picks the minimum and it puts it in the right place. But I would always forget that insertion sort drags an element back into its position. Okay. Merge sort, on the other hand, let's look at merge sort. So here's a list. And let's just see what merge sort does on this list. So what I'm going to say that merge sort is going to do, before I start running it, because I'm not sure how, well, I'll slow it down just a little bit the first time. It's going to break the list into 2 halves. And then it's going to call merge sort on the first half, it's going to call merge sort on the second half, and then it's going to kind of concatenate them back together. But then you see that this half has to be, in fact, it does involve recursion, because if I tell you that you have to, in order to merge sort something, you take the first half and the second half of the list, right? Then how do you sort this list or this list, right? You also have to break those lists in half and, Vulcan sign. And then and then you have to merge sort those lists. And then finally, you break those lists in half to get all the possible, I'll just fold my thumb in, to get all the possible lists. You merge those, and then finally, when you have to put everything back together, these are all sorted lists, right? These are all sorted lists. So in order to merge them back together, you have to have some algorithm that does that. And then you merge these back together, and then you merge these back together. So that's how a merge sort works, right? At first you break up, you break up, you break up, and then you merge, merge, merge. So, okay. Let's watch it do it. Let's go. So, okay, so this visualization is kind of a little bit confusing. So let me just show you what they did here. So this was just sorting this part. So the next sublist that they're going to sort is going to be these two, and then they're going to sort these two, and then they're going to merge these back together. So let's watch that happen. So they're going to flip this one and this one. They're going to flip this one and this one. And what this doesn't really show very well is it doesn't show the splitting up of the list, right? But now, right here, we have 2 sorted sublists, and we have this part that hasn't even been touched yet. So what the next part of merge sort is going to be, so what this is doing is basically it's split up the first part of the, or let's do it this way, it split up the first part of the list, it split up the second part of the list, and now it's merged those parts back together, and now the last step is that it has to merge these parts back together, and then it has to merge sort this side. So it's doing it in a different order than I'm basically talking about, but it's doing the same thing. So here it's going to now merge these two. So it's going to take 3 and 5, and then it's going to take 15, 26, 36, and then it's going to take 38, and then 44, and then 47, right? So it's going to merge them back together in that order. So we'll talk about how the merge process works. So now you see that the first half of the list is sorted. So now it's going to do the same thing, but now to the second half of the list. This is like the second part of the recursion. So it's going to sort these two, then it's going to sort these two, then it's going to sort these two, but it's already, well, okay, that's kind of, okay, so I guess the question is, why didn't it touch anything here? The reason why is because 19 is less than 50, so it didn't have to sort it. And this is the odd man out. 48 is not part of any of the other lists, so it just gets kind of tacked on at the end. So now it's merging back together this part. Well, actually, the big O of this merge sort is, it's probably harder to, well, no, it's not harder to calculate. It's actually, it's, well, yeah. We'll explain how to calculate it in just a second, but first we have to implement it. So I've already written the merge algorithm, which is usually pretty easy to write. And then I'll write the merge sort algorithm in just a second. So, okay, cool. So this is how everything worked out. It merge sorted the list. Cool. And I'm not going to do any kind of optimizations. I'm not going to be smart. We're just going to do it in kind of the most simple way we can think of. So let me show you the merge part of the algorithm. So, and I'm being probably too tricky here. I was thinking, oh, I'll be tricky. Let's not be tricky. So I always hate when people do this anyway, so I'm going to not do this. I did this last night because I don't know why. Okay. So you can, if you want, put the plus plus in here. Actually, I tend to recommend, I know that if you're like elite C++ coder, you're going to be like, there's no problem, I completely understand what's going on here. But remember that, like, when the next person comes around to read your code, they might not see this plus plus operator in here, and then they will be confused as all heck about what's going on, right? They'll have to look through your code much more carefully, and then they'll finally find it, and then they'll basically like, someone thought that they knew C++, someone thought they were going to be tricky, and I got tricked because I didn't see it. So I'll take that out. Anyway, so here's how merge works. Basically, this is not merge sort. This is just merge. So what merge does is it takes two sorted sublists. So that's the requirement here. The requirement is that these sublists have to be sorted. If they're not sorted, then basically this does nothing. This basically is like garbage in, garbage out, right? If they're not sorted. Okay, so it takes two sorted subvectors, subarrays, sublists, whatever you want to call it. And so what it's going to do is it's going to give us back a sorted sublist made of both of them. So let's think of how merge has to work, right? What merge has to do is it basically has to go through the sublist and be like, here's the starting elements. Here's the starting elements, right, in the list. Who's bigger? Who's less? Whoever's less goes into the overall list, and whoever is bigger doesn't do anything yet. And then you check the next element. Are you bigger? Or are you less? And so if you're less, then you go into the list and you do nothing. And so finally, if you do this, and this is less, then it goes in and you look at the next element, right? So basically what you're doing is you're just picking the smallest of the two elements from both lists until we run out of elements in the lists. So let's go through how this works. So what we're going to do here is we are going to go through, I have while index 1 is equal to 0, index 2 is equal to 0. And while index 1 is less than v1.size and index 2 is less than v2.size. So what this is going to do is it's going to go as long as both lists have something in them, right? And so what I'm going to do is I'm going to say if v1 at index v1 is less than v2 at index v2, then we take that element and we add 1 to index 1. Otherwise, we take the thing in list 2 because it's less and we increment index 2. And so you see that at some point, right, this is okay to do because at some point, one of these is going to hit the index of its list, right? One of them is going to hit the list size. And then what happens then? So basically, here's an example where, so if we're merging the list like 2, 5, 7, 9, and like the second list is 1, 3, 8, 10, then the merged list is first it's going to take 1 out of this list, then it's going to take 2, right? It's going to take 1 and then it's going to advance its position. So then the position is now here, right? So our position is here, and then it's going to advance. And then 2 is less than 3, so it's going to take 2, and then it's going to advance this to 5. And then it's going to take 3, and it's going to advance this to 8, right? And then it's going to take 5, and advance this to 7. And then it's going to take, so then you see why we need to do this while loop, because it's going to take 7 again. So it's not going to take this thing out of the other list, it's going to take the 7 now. And so then it's going to take 8 and advance. And then finally it's going to take the 9 element, and then now it advances, but now it's past the end. So now we don't use this code anymore. Now we have to use this code here. And you see what this does. This is just really simple. All it does is it says, if the index 1 is still less than v1.size, push back everything that's left. Well, as it turns out, index 1 in this case is equal to v1.size, so this loop is actually not going to run in our example right here. But let's look at the second loop. So the second loop says, while there's still stuff in the second list, take the elements in the second list and add them on, and then finally just return the answer. Right? That's it. And so right in here, it's going to take the 10. It finally pushes past the end of both of the lists, and now it is done, right? And so another example, for instance, is if you have like 2, 2, 2, 2, and let's say you have 5, 5, 5, 5. So we start with something like this, right? And what we're going to see is that the first thing it's going to do is it's going to take 2 and move. And then you're like, well, 2 is still less than 5, so it's going to take 2 and move. And you're like, well, 2 is less than 5, so take 2 and move. And you say to me, I don't know, 2 seems less than 5 again. Okay, 2, and then end of list, right? So that's the end of the first part of this code here. So it breaks out of this loop because index 1 is now past the length of the list, or equal to the length of the list, or whatever. And so here, it's going to skip this thing, and now it's going to start taking things from the list 2. So it's going to say 5, 5, 5, 5, right? And it's going to advance this here, 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 and finally here. And so after it's done this loop, now you have 2, 2, 2, 2, 5, 5, 5, 5. So this is definitely another way that it can go through a list, basically, and then so now it is sorted. And so you see that this merge algorithm, it doesn't care how the lists are structured, right? It'll merge them back together either like this, or however, until it's right. So it'll make sure that it never sticks an element that's bigger later. And so that's exactly what we want. So it takes 2 sorted sublists and it makes a a sorted list. There we go. Okay, so now that we understand merge, how do we do the merge sort? So here's merge sort, and obviously I haven't done much with it yet. So so we're not going to do the heap sort, so nope. I'll just even delete that. So basically what we need to do is we need to make the front list half of the list. So for int I equals 0, I is less than list to sort dot size divided by 2, right? And then I plus plus. So this will take the list in the first half, front list, dot pushback, list to sort, come on, autocomplete please, at I. Wow. So this is just copying the front list, Now we can copy the backlist. So there's ways to do this better, but I am not going to do this better. We are going to do this exactly, for int j is equal to list of sort dot size divided by 2. We have to be a little bit careful here, but here it's going to take, and then j is less, I think this will be okay. J is less than, list of sort dot size, and then j++, right? And so then the backlist, okay, I will spell back correctly, backlist. Yeah, what happens if the number of elements is odd? That's a good question. So what's going to happen in this case is it's going to break it down, I think. And so, well, actually, you can just kind of think about it this way. So if the number of elements is, say, 5, then list of sort is 5 divided by 2, right? So here it's going to take the rounded down version, because remember that these are integers. So it's going to round all this stuff down. And so it's going to take the, it's going to take this divided by 2. So 5 divided by 2 is 2. So I is going to go from 0 to 1, so it's going to take the first 2 elements. And then the backlist is going to take the rest of the 3 elements. And so basically you're going to end up with a split like this, so a list like this going to something like that. And then when you merge sort this part's going to do okay. And then this part is going to split itself off. Well, let me try not to accidentally do anything too vulgar. But then, yeah, it'll split off the last element, and that element's already merge sorted because it's on its own. And then these 2 elements get merge sorted, and then it mushes it back together. Okay, so j minus... Oh, no, I'm sorry. Oh, cool, we don't actually have to do... We can just use pushback. See, you know what? I didn't realize that I was going to be smart. I thought I was going to do something stupid, but I actually did something not terribly stupid. Maybe not the most stupid thing. I mean, still pretty dumb. It's inefficient to copy these lists, right? That's what I'm saying about this. It's inefficient to have to copy these over and over. The good news is it doesn't actually affect the big O complexity of this algorithm, but it does kind of add an extra multiplier. So that's unfortunate. But c'est la vie, right? Okay, so let's finish the implementation of merge sort. So the cool thing about merge sort is that now what we get to do, and remember that these are not actually being returned, so we can merge sort the front list, we merge sort the back list, and then we merge the front list with the back list. God, I was talking and typed with. But anyway, do you see how this kind of works, right? We make these copies, right, of the front part and the back part. And then we merge sort the front part. So now, once this is done, right, we get to assume that the front part is sorted. Now you might think to yourself, I'm afraid, right? You just have to trust the recursion, right? Because this is a recursive function. What it's doing is it's saying, okay, you want to merge sort a big list, you call merge sort on the front half of the list. And then it calls its merge sort on the front half of the list. And it calls its merge sort on the front half of the list. Until the base case of the recursion, right? What does the base case of the recursion do? If the list of sort size is bigger than 1. So either you get an empty list where the list of sort is 0, which is okay, right? An empty list is a sorted list. Or you get another type of list, which is a singleton list. A singleton list is also sorted, right? Because it doesn't have any elements to compare it to. Now, a duplex list, a dyadic list, a list of 2 elements, is potentially flippable, right? You could do a swap algorithm maybe for that. Like, you wouldn't need to use merge sort. Like, you could say, if it's bigger than 2, and then you could say something like else, right, if the list of sort, dot size is equal to 2, then do some swap, right? Or something like that. But that's adding some complexity to this algorithm to optimize it that I'm not going to do. I'm just going to leave this completely unoptimized. You can always think of things to optimize these things, right? So this is not like the best way to do merge sort that I've ever seen. But the good news is for educational purposes, it is perfectly fine. So here you can say, now we can assume that the back part of the list is sorted, right? I guess merge actually returns the list, so merge will set list to sort equals merge. So that should fix the problem that I was about to create. Or technically you might have to copy it. This might create a problem. This might be a bug. So, anyway, okay, so we assume that the front part of the list is sorted, we assume that the back part of the list is sorted, and then we merge it and we set it back into this thing. So I guess technically we could even just make this this, and then we could just return. And that would definitely fix it. Now it's not. So I'm going to remove this comment. Okay, so the cool thing is this, and otherwise you just return list to sort. Like that. Okay. So this is why this algorithm is so great, is because what it does is basically what it has to do is it breaks. Okay, so let's analyze the big O complexity of this thing, right? So that now it's time to analyze the big O complexity of merge sort. So the nice thing about the big O complexity of merge sort is that really all you have to do is you draw out the algorithm. So the algorithm takes a list, and let me draw my no box, no, and it'll break it in half, right? So this is half the list, this is half the list, right? Well, let me make this list a bit longer so that it's about the same. Okay, so it takes a list and it breaks it in half. And then it breaks it into 4 parts, right? This is what the merge sort process does, right? This is like calling merge sort on each of these parts, right? Merge sort, merge sort, merge sort, merge sort, all the way down, right? Until when, right? When does it stop? So when does this process stop, right? And the answer is, yeah, when there's 1 or 0 elements left. So when these things are of size 1 or 0, and you could say or size 2 or whatever, but again, let's just say if they're of size 1 or 0, then it stops. So yeah, exactly. So yeah, every time the list size is dividing, right? So when there's a single element left, that's when it stops. So how do we deal with that? So, and then remember that what happens after it merge sorts, let's say that here these are down to singleton elements. So every time it's dividing it by 2. So the list size is divided by 2 here. The list size is divided by 4 here. It's divided by 8 here, right? The next one would be the list size is divided by 16, 32, 64, right? So basically what I'm saying is that it's n divided by 2 to the number of steps. It has to be somewhere between 1 and 0. So that means that n is less than or equal to 2 to the number of steps, which means, and this is the exciting part, right? How do we solve for the number of steps? Right? How do we solve for the number of steps? Ooh, this is exciting. We get to take LG of both sides. LG. Remember, LG is log base 2. It's also a, Korean phone company? But it's also log base 2, which is the which is the good stuff. And so, yeah, so this is log base 2. So it takes lg of n steps in order to complete. So this whole process takes lg of n steps. Now the question is, what is the process at each step, right? That's now the question. So you notice that here we have 8 lists of size n over 8. And we have to merge them all, right? We have to copy them, and then we have to merge them. And so remember that merge is just a loop that's going to go through 2 lists. It's going to go through 2 lists of size n over 2, and it's going to give you a list of size n. And so the complexity of that is O of n. So basically every merge algorithm this is like 8 times O of n over, well, it's really 4 times, because you have 4 pairs, O of n over 4. This is 2 times O of n over 2, basically, more or less, right? But let's get rid of the big O. Let's just say it's 2 times n over 2. This is 4 times n over 4. The next one will be 8 times n over 8, right? Yeah, I think we might be getting into the Highlander business, right? You know. So, okay. So my point here is that 4 times n over 4 is equal to n. 2 times n over 2 is equal to n. This is this is basically one merge, right? This is 2 lists of size n over 2, but it's 1 merge of size n. That's what I'm doing to calculate here. So 2 lists of n over 2 is 1 merge of size n. This is 2 merges of size n over 2. This is 4 merges of size n over 4. The next one would be 8 merges of size n over 8. Well, the good news is that 4 times n over 4, it all cancels out, right? We're so happy because this all cancels out. And so what we know is that merge sort is always going to take n times the log of n steps. So it's big O of n log n. It's also omega because it can never do better, right? It doesn't care. Did merge sort care about the structure of the list? It cared if there was an even number or odd number of elements a little bit, but it did not care if the lists were sorted, unsorted. It didn't make a mention of anything, right? It just said, I'm going to split the list, right? It didn't check if it was sorted first. It didn't do anything. It just says, I'm going to split you. If you are sorted, I'm going to split you. If you're unsorted, I'm going to split you. And then I'm going to put you through the merge sort algorithm, and then at the end, I'm going to merge you. And if you're sorted, then you're going to come out sorted, and I'll merge you. And if you're unsorted, then you're going to come out sorted, and I'll merge you, right? So merge sort does not care, right? Merge sort does not care about the structure of the list. So that's one important thing about merge sort, is merge sort does not care. About list structure, which means that it's O of n log n. But you can also say that it's omega of n log n. Ooh, didn't realize it was going to storm. Either that or someone just crashed a truck into my house. Yeah, one or the other. Yeah, no, it is a little bit of a threat. Merge sort is like, I'm going to merge you and I don't care, right? So, okay, cool. Because it's both of these, it is now this. Okay. So, what else is there to talk about? Well, there's quicksort. Maybe I'll make a separate video about quicksort. I'll just make a separate little lecture about it. or you know what, maybe we will just do quicksort now. It's okay. Couldn't you add a case to check if it's sorted? Aha, that's an optimization. Yes, you could. In fact, while you're doing the splitting of the list, right, because that's an O of n process, you could, for free, check if this list is sorted, and if it is, then don't call the merge sort algorithm, just return it. That is completely fine. That's an optimization. I didn't do that because, you know, I think the reason why is because when I post this code to GitHub, I want this to be the most simple version of the algorithm that I can come up with. I don't want it to be a version of the algorithm that's going to be like, oh, what's this extra little bit doing, right? You should be able to say, we split the lists using this part of the code, we merge sort the front of the list, we merge sort the back of the list, and then we merge it back together in return. And that's exactly what this algorithm does, right? Of course I should test it all out, but I'm not going to do that because it's probably going to be buggy and not work or something. Like I'll have like a less than or equal to sign somewhere where I should have an equal to sign or something horrible and we'll get seg faults. I might test out the code after class or something, but yeah. Okay, so the last thing to talk about, and I don't know if you guys are willing to stick with me for maybe another 15 minutes. I hate to do it, but the problem is online Eric is very slow. He doesn't cover as much as he needs to cover. I don't know whether it's I'm explaining it to myself and I'm going slowly. I don't know what is causing this problem, but I noticed that in 201 and in 341, every class, and in 203 when I taught 203, I'm just slow. It's terrible. I hope you guys don't mind. I hope you're understanding what I'm actually saying and we're all working together. So if you would give me the extra time, if you don't have the extra time, then just watch this later. Let's talk about quicksort. It's okay if you have to go. It's okay if you have to go. I just ask you eventually, maybe if you're interested, watch this about quicksort, because unless of course you already know quicksort, and then you can just skip it. Okay, so yeah, I think it is. So Stephen, I think you're right. It's partially because I'm just talking to a wall, and I'm like, am I making sense? Am I not making sense? Who knows? I think you would have to set the front list equal to merge sort of front list. No. So I return, so they're references, right? And so I think merge will, merge sort should, yeah, you might have to return that. Okay, I mean, I'll fix it. I'll fix it eventually. Okay, so let's talk about quicksort. So what does quicksort do? Quicksort usually makes 2 buckets, but I prefer 3 buckets. So here's bucket 1, here's bucket 2, and here's bucket 3. So we have a list of elements, and we have a pivot element, okay? Now, there are better ways to do this, but the usual way to teach quicksort is you pick the pivot is equal to the first element of the list. So list sub 0, right, is just the, whatever list sub 0 is, if this is list L, then list sub 0 is just the pivot. Now the question is, what is the pivot? The pivot is an element that we check all the other elements against. And so there's 3 buckets. The one bucket I have here is the less list. And I'll call this the equal list. And I'll call this the greater list. And so basically what you do is if the element is less than the pivot, you shove it into the less list. If the element is equal to the pivot, right, you shove it into the equal list. And if the element is greater than the pivot, you shove it into the greater list. Now, we're generally going to assume for most of our stuff that the equal list is either just the pivot or relatively small, that most of the time that the lists are going to be partitioned mostly into the less list and the greater list. but whatever. So it could be partitioned equally into 3 parts, which is actually a little bit better for us because we don't have to sort this one. So then quicksort, what quicksort is going to do is quicksort is going to sort this list, sort this, right? Quicksort this. You don't have to quicksort this, we're good. And you can quicksort this. So, and then the point is that you can, after that's done, what you get to do is you get to do some list concatenation. So you just add these lists back together once they're sorted. So that's the idea of quicksort. You break the list down into the things that are less than the pivot, equal to the pivot, and greater than the pivot. And then you quicksort the things that are less than the pivot, you quicksort the things that are greater than the pivot. So then once these quicksorts are done, right, once these quicksorts are done, you assume that this is now sorted. This is now sorted. And so then, yeah. Okay. So let's write the code for this. So how does this work, right? So let's write the code. There we go. The nice thing about quicksort is that it doesn't need any helper functions, so that's nice. If the list to sort is of size bigger than 1, then we can quicksort it. Else, let's just return Python again. Return list to sort. Okay. So what if the size is bigger than 1? So then we pick the pivot is equal to list to sort 0. And then for I equals 0, for int I, so I don't want to talk about bucket sort when I'm talking about quicksort, because quicksort only calls quicksort recursively. You could create a quicksort bucket sort merger that detects whether it's better to do a quicksort or a bucket sort, and then does the better thing, and that would be great. But then you're neither doing a quicksort nor a bucket sort, so I'm just going to stick to quicksort for here. Oh, and I totally forgot. C++ does like list iterators now, doesn't it? Oh, well. Okay. Maybe I'll do that next time. So that's the problem with knowing like C++ from like 20 years ago, is that a lot of these new features weren't implemented. But anyway, it doesn't really matter. So let's create 3 new lists. So vector int less list, vector int equal list. Basically, the equal list is just keeping track of the number of times that we find the elements that are equal. Greater list. So if, right, the element list to sort at I is less than the pivot, then we stick it into the less list, right? Nope. I'm sorry, guys. Okay. Else if, see, I did that right. I didn't do anything stupid there. Else if it's, say, bigger than the, let's just say it's equal to the pivot. Then we'll push it back into the equal list. So I'll copy paste that into equal list. And then we'll do else, right? Else, we can say else by the law of trichotomy, right? Is that either if you have x and y are integers, then either x is less than y, x is equal to y, or x is bigger than y. Otherwise, it's a little bit dangerous, right? Okay, cool. And so that's really it, right? And you see that this is definitely O of n, right? And the reason why it's O of n is because we have to go through every element of the list, right? And we only ever evaluate exactly one of these statements, and these statements are basically each O of 1. So O of 1 times n is O of n, and there we go. So, but we're not finished with the whole sorting algorithm, because you're like, wait a second. Wait, we never sorted the sublists. So what we get to do here is we can say less list is equal to quicksort less list, because now remember we're returning things. Greater list equals quicksort greater list. And am I mistaken? I think vector has an overloaded plus operator, right? You can do this, right? I think you can do this. Oh, maybe you can't. All right, well, if you can't do that, then what you get to do is the stupider thing. You get to say, you know, yeah, you can either stick them in the less list or the greater list. The reason why I do an equal list is actually because sometimes you can run into conditions where if you have a whole bunch of equal elements that all keep getting shoved into the same list, it does make it a lot worse in terms of the runtime. So this is actually, I mean, I know I said I'm not doing optimizations. This is sort of an optimization to prevent one really stupid case from like causing mega devastation to your algorithm. Is that how the iterators work? And you can do I think that's how the iterators work. And finally, for z in greater list, total list dot pushback z. So, you know, if we just overloaded the plus sign, we wouldn't need to do any of this, but whatever, we could. So this just basically sticks all the less stuff on the front, and then it puts all the equal stuff next, and then it puts the greater stuff at the end, and so then it is done. So this is the implementation that I would probably, well, this is an implementation of, you don't need it. It's a slight op. So, okay. Why don't we analyze the complexity of this next time? So the cool thing about quicksort is that it has a different best case, worst case. It has different cases. So I'm just going to tell you what those cases are, then I'll end class. But the best case is basically O of n log n, and the worst case is O of n squared. So actually you might even be forced to call this a quadratic sort. But the expected case, so like the amortized case, is O of n log n. So except for in really bad cases, and I'll tell you what those really bad cases are next time. I'll tell you now, and then we'll talk about it more next time. So a reversed list is generally, I think, the worst, because it will force you to, oh no, I'm sorry, not a reverse list. A reverse list will actually, oh no, a reverse list is bad, but also equally bad, and this is kind of unfortunate, a sorted list is also bad. Because if you think about it, what is a sorted list going to do? the pivot is the smallest element. So the less list is never going to exist. The equal list is going to be one element, or maybe all the times that the pivot occurs. So it's going to be a few elements. And then the greater list is going to be most of the list. And then when it goes to into the next quicksort, the most of the list is going to go into the greater list, and it's going to get quicksorted. And then the next element is going to be, like if you have a list of 1, 2, 3, 4, 5, yeah, so any list where the pivot is reliably close to the end, we can construct some really bad lists based on this. And there's actually ways to fix the pivot so that it doesn't do this. Actually, the right way to fix the pivot is to use a find median algorithm, which runs in O of n time, which is okay because then this partition is also O of n, and it can prevent the worst case. So this does actually prevent the worst. If you use a special find median algorithm, it can prevent the worst case from happening, and you can get O of n log n guaranteed. But this algorithm as written right here, and quicksort as it's described on Wikipedia, in textbooks, in our textbook, in any textbook, the worst case is n squared because they don't make that optimization, at least at first. So they sometimes make that optimization, and once they do, then it runs an O of n log n guaranteed. And just one last thing before we go. I think the last thing is, let me just show you n squared versus n times log of n. And let's reset the So here is n squared, and here is n log n. And so let me just show you what happens. Let's make x go out to, say, 100,000, and I don't know, n squared is going to have to go up to, like, I don't know, something like this. So let me just show you why n squared is worse. This is the amount of time it takes, right? Here's n log n, nicely chugging along, and here's n squared, blasting off to infinity time so much faster than n log n that it's hard to even put the two graphs in the same window, right? And so this is why people prefer merge sort or quick sort or heap sort when we get to it, when we talk about heaps, because those sorts that give us the n log n time, look how much time this saves us. This saves you basically a lifetime's worth of time. Like you know, a list that you can sort in an hour here would take you like the rest of your life if you did it with an n squared sort. So that's why computer scientists prefer n log n to n squared, because n squared explodes. N log n also goes to infinity, but it goes to infinity in a much more controlled way. This is a way that you can live your life. This is a way that you'll be waiting forever. Okay? All right, so I think that is the end of this lecture. I'm sorry that I took more time than I should have, but you know what? I'm glad that I did quicksort. So next time on, CMSC 341, I will discuss the homework. I'll probably release the homework Friday. So next time we'll talk about the project. We'll talk about the project 1, which is way in the future. We'll talk about homework 1, which I will write. Okay, that didn't work. There we go. That is nothing. And then we will do binary search trees at the... am I available for help on Project Zero? Sure, I can be available today and tomorrow. Yeah. Maybe I'll make like a help channel on the Discord, and oh, and I figured out how to add people on the Discord. So if you need a Discord invite, send me another email, and I will give you another Discord invite, and then I will change your status, and then yes, and then I'll talk about Project 1, Homework 1, and then I would like to talk about the analysis of quicksort. Okay, So, and then we'll do binary search trees. We'll do like the theory of binary search trees. And then on Thursday next week, we'll do the implementation. So I think that's a good step for next time on Tuesday. I'll probably get some of this done. Who knows? Okay. Nice. All right, I will see you people in our next episode. I hope that everybody learned a little bit about merge sort and quick sort. Yeah, linked lists are kind of like that. They're kind of an interesting data structure because they're kind of easy enough to teach to a 202 student, but then there's also kind of 341 aspects to them as well, which we'll talk about in the homework and stuff like that. But, you know, it's definitely the first data structure that you want to analyze because it's kind of the simplest. Like, all data structures in this class are essentially bubbles with arrows, and like a binary search tree, right, is like bubbles with arrows like this, and a linked list is bubbles with arrows like this, right? So basically it's just how do you do the arrows between the bubbles? Like, what shape are the things? So yeah, that's also true. Linked lists are kind of, it is very rare to find a linked list out in the wild that's actually doing something that's like, you know, you want to be careful with linked lists because obviously even a search of a linked list is O of n. Okay. All right. Well, I'm going to let it go at that. I think that we've said all we need to say. I'll upload this code now that it's kind of finished. I'll upload it to the GitHub, and that is it for the day. So have a good rest of your day. If you need any help on Project Zero, send me an email or contact me on the Discord. If you send me a DM on the Discord, make sure you say that you're a 341 student, because I have so many 201 students DMing me that it's really hard to sort out who's who. And if someone just says hello, which I've had a few people do yesterday, I was like, hello, who are you? What do you want? Like, come on, like, tell me. Be like, I'm a 341 student and I need this. I'm like, cool. If you're like, hello, I'll be like, hello. So, all right. I'll talk to you guys later. Get your Project Zero submitted, and if you can't, then we'll work together. All right. That's it.